For decades, each new world discovered beyond our solar system felt like a step towards something, another planet out there, another candidate, another reason to believe the universe had not left us entirely alone. Then the James Webb Space Telescope began looking more carefully, not at whether alien worlds existed, but at what those worlds were genuinely like. And what it found was not what anyone had prepared themselves to hear. Webb peeled back the atmospheres of distant planets and found storms of sulfur dioxide, skies where silicate particles rained down like hot sand, temperatures so savage they destroyed molecules at the atomic level, and surfaces scoured clean of any protective envelope of gas. The assumption had always been that better telescopes would bring better news. More detail would mean more familiarity. A clearer view would reveal friendlier worlds. The reality moved in exactly the opposite direction. The more precisely we observed alien planets, the harsher and stranger they became. The universe is filled with worlds. They are simply nothing like home. If you want to understand what the James Webb Space Telescope is genuinely revealing about the planets beyond our solar system, consider hitting that like button and subscribing. It costs nothing. It helps this channel keep bringing you the stories about the universe that actually matter. Now, settle in and get yourself comfortable. Let's begin. There is a question that has followed every generation of human beings who ever tilted their heads toward the night sky. Are we alone? For most of recorded history, the question had no answer. Stars scattered across the darkness in their thousands, thrown like sparks against black cloth. Whether those stars carried planets around them, whether those planets held oceans or soil or air, whether anything had ever drawn breath on any of those distant points of light, there was simply no way to know. The stars were silent and beautiful and unreachably far. The question hung there, in the dark, century after century, without a single piece of evidence pointing in either direction. Then, in 1995, everything shifted. Michel Mayor and Didier Queloz, two Swiss astronomers working at the Haute-Provence Observatory in the south of France, announced the first confirmed detection of a planet orbiting a sun-like star outside our solar system. The star was called 51 Pegasi, an ordinary yellow dwarf sitting roughly 50 light-years from Earth in the constellation Pegasus. The planet, designated 51 Pegasi b, was nothing like what the scientific community had anticipated. It was a gas giant, roughly half the mass of Jupiter, yet it completed a full orbit in just 4.2 days, hugging its parent star so tightly that its surface temperature likely exceeded 1,000 degrees Celsius. This was not the kind of world theorists had expected to find first. Models of planetary formation predicted that giant planets should form and remain far from their stars, the way Jupiter and Saturn occupy the cold outer reaches of our own solar system. A massive gas planet practically grazing its host star seemed almost contradictory, but the data left no room for doubt. The radial velocity measurements were unambiguous. The planet was real. That single discovery opened a door that could never be closed again. Within months, other research teams confirmed additional detections. More hot Jupiters appeared around other stars, then smaller planets, then planets in wider orbits. Each announcement sent a current of excitement far beyond the walls of professional astronomy. Newspapers ran headlines about new worlds. Documentary filmmakers speculated about alien civilizations. The broader public imagination caught fire because the implication was immediate and irresistible. If planets were out there, and they demonstrably were, then perhaps some of them resembled Earth. Perhaps some had continents and weather and liquid water pooling in low places. Perhaps somewhere among the stars there were surfaces a human being could stand on, air a human being could breathe, a sky that looked unfamiliar but felt like sky nonetheless. That hope was not irrational. It rested on a chain of reasoning that felt almost mathematically inevitable. The observable universe contains somewhere in the vicinity of 2 trillion galaxies. Our galaxy alone holds approximately 400 billion stars. If even a modest fraction of those stars hosted planets, and if even a small percentage of those planets occupied the right orbital distance from their star for liquid water to exist on their surfaces, then the sheer scale of cosmic numbers practically demanded that Earth-like worlds existed somewhere out there. The arithmetic was so vast and the logic so clean that the only real question seemed to be when we would find one, rather than whether one existed at all. The late 1990s and the early 2000s became a period of accelerating discovery. Astronomers refined the radial velocity technique, which detects planets by measuring the gravitational wobble they induce in their parent star. A planet orbiting a star does not simply circle a stationary object. Both the star and the planet orbit their shared center of mass. The star traces a small ellipse in response to the planet's gravitational pull, and that motion shifts the star's light fractionally toward blue when the star approaches us, and fractionally toward red when it recedes. By measuring these shifts with extraordinary precision, astronomers could infer the presence of an unseen world and estimate its orbital period and minimum mass. But the radial velocity method had firm limits. It worked best for massive planets sitting close to their stars because those produced the largest detectable wobble. Smaller planets at greater distances created signals so faint they vanished into noise. More fundamentally, the method was indirect. It told you a planet existed and gave you some orbital parameters, but it revealed almost nothing about the planet itself. You could estimate mass, you could calculate orbital distance, you could derive a rough equilibrium temperature from the star's luminosity and the planet's separation. But you had no idea what the atmosphere contained, what the surface pressure was, whether the planet had clouds or chemistry, or any of the conditions that determine whether a world is hospitable or lethal. The planet was a gravitational inference, a mathematical shadow cast in starlight. It was real, but it was invisible in every way that mattered. This limitation mattered more than most observers appreciated at the time. The public conversation about exoplanets moved faster than the science supporting it. Every new detection was reported as though astronomers had found a destination, a place with describable features and imaginable landscapes. Media coverage routinely included artist renderings depicting blue oceans, green coastlines, and layered clouds on planets that had been detected only as periodic oscillations in a star's velocity curve. The distance between what was actually known and what was being vividly illustrated grew wider with every headline, but no one minded, because the story was too compelling to slow down. Then came Kepler. Launched by NASA in March 2009, the Kepler Space Telescope was designed to address one of the most fundamental open questions in all of astronomy. How common are planets? More specifically, how common are small, rocky, potentially temperate planets orbiting sun-like stars? Kepler pursued this question using the transit method, a technique that detects planets by watching for the slight dimming of a star's light when a planet passes in front of it from our line of sight. When a planet's orbital plane happens to be aligned so that it crosses the face of its star as viewed from Earth, the star's brightness drops by a measurable fraction for the duration of the crossing. The depth of that dimming reveals the planet's size relative to the star. The regularity of repeated dimmings reveals the orbital period. Combine those measurements with knowledge of the star's properties, and you can calculate the planet's distance from its host and estimate its surface temperature under simplified assumptions. Kepler fixed its gaze on a single patch of sky in the constellations Cygnus and Lyra for nearly 4 years, monitoring the brightness of more than 150,000 stars simultaneously, sampling those brightness values every 30 minutes with a precision that had never been achieved from space before. It watched for the tiny, regular dips that would betray orbiting worlds. The results were staggering in their scale. By the time Kepler's primary mission concluded in 2013, it had identified thousands of planet candidates. Confirmed detections eventually surpassed 2,700, and statistical analysis of the full dataset suggested that confirmed planets represented only a fraction of those actually present within its field of view. The numbers Kepler produced fundamentally reshaped our picture of the galaxy. Rocky planets were not rare. They were common, far more common than the gas giants that had dominated early detection catalogs. Planets between 1 and 1.5 times Earth's diameter, a category scientists called super-Earths, appeared around roughly 1 in 5 sun-like stars. Many of these planets orbited within what astronomers called the habitable zone, the range of orbital distances where a planet receives enough stellar energy for liquid water to exist on its surface under certain conditions. Extrapolating from Kepler's field to the full galaxy, researchers estimated that the Milky Way might contain billions of rocky planets within habitable zones. Some calculations placed the number above 10 billion. Others were more conservative, but still arrived at figures in the hundreds of millions. The effect on the public narrative was profound and lasting. The habitable zone, originally a technical term from planetary science describing a geometric band defined by a star's luminosity, migrated out of scientific literature and into everyday vocabulary. News articles routinely described newly discovered planets as sitting in the habitable zone, as though the phrase were synonymous with the word habitable. The distinction that scientists understood clearly but rarely had the opportunity to explain in a headline was enormous. The habitable zone is a calculation about orbital geometry. It describes where a planet sits relative to its star's energy output. It says absolutely nothing about whether the planet has an atmosphere, whether that atmosphere traps enough heat or releases too much, whether the surface is liquid water or liquid rock or frozen methane, or whether any condition exists that is remotely compatible with biology. Being in the habitable zone is something like standing at the right distance from a campfire. You are not close enough to burn and not far enough to feel nothing. But that tells you nothing about whether you have shelter, food, or any other requirement for surviving the night. In the public narrative, however, the habitable zone became a near synonym for habitable. Mission proposals leaned on it. Funding justifications built around it. Popular science books dedicated entire chapters to it. The phrase appeared in thousands of headlines across the decade following Kepler's launch, almost always in contexts that implied far more than the underlying science supported. When a planet was announced as rocky and in the habitable zone, the unstated message was clear. This could be another Earth. The qualifications that scientists carefully included in their papers, the caveats about unknown atmospheres and uncertain surface conditions, rarely survived the journey from journal to headline. Venus offers the most instructive illustration of this problem. Venus orbits near the inner edge of our own sun's habitable zone. It is almost exactly the same size as Earth. Its mass and bulk composition are similar. By the transit metrics Kepler used to classify planets, Venus would register as one of the most promising Earth-like candidates observable anywhere. A rocky world nearly identical in diameter to our own planet, sitting within the habitable zone of a sun-like star. If an alien astronomer using Kepler-equivalent technology detected Venus transiting our sun from 50 light-years away, they might reasonably flag it as a high-priority target for follow-up. They would be catastrophically wrong. Venus has a surface temperature of approximately 465 degrees Celsius, hot enough to melt lead. Its atmospheric pressure at the surface is 92 times that of Earth, equivalent to the crushing weight you would experience nearly a kilometer below the surface of our ocean. Its atmosphere is 96.5% carbon dioxide, saturated with clouds of sulfuric acid. Its surface is a geologically violent wasteland where no known life could endure for even a fraction of a second. Venus is not merely inhospitable. It is one of the most aggressively hostile environments in the entire solar system, and from the perspective of transit detection, it looks almost exactly like Earth. This example encapsulates the central problem that defined the entire era before Webb. Detection tells you that a planet exists. It gives you some basic physical parameters. It does not tell you what the planet is actually like. The gap between a rocky planet in the habitable zone and a place where a human being could stand outside and breathe is not a minor technical detail to be filled in later. It is an enormous chasm populated by atmospheric chemistry, thermal dynamics, stellar radiation history, geological evolution, magnetic field strength, and dozens of other variables that transit photometry alone cannot measure. For 2 decades, the exoplanet field operated largely within that chasm, generating data that was scientifically rigorous but emotionally misleading, because every detection fed a hope that the detection itself had no power to validate. By April 2018, NASA had launched the Transiting Exoplanet Survey Satellite, known as TESS, designed to survey nearly the entire sky rather than Kepler's single fixed patch, monitoring the nearest and brightest stars for transiting planets. TESS was explicitly conceived as a bridge to the future. It would find the best candidates, the closest and most accessible planetary systems, and a future telescope, the James Webb Space Telescope, then still years from launch, would follow up with detailed atmospheric analysis. TESS was the scout. Webb would be the analyst. TESS delivered precisely what it promised. Within its first 2 years, it confirmed hundreds of planets and flagged thousands of candidates. Many were rocky worlds orbiting nearby red dwarf stars, precisely the category of target that Webb's instruments were best equipped to study. The TRAPPIST, one system, discovered in 2017 by a ground-based survey, became a sensation with its 7 approximately Earth-sized planets packed into a remarkably compact orbital architecture. Lists of Webb-accessible targets grew longer with each new confirmation. Each rocky planet found around a nearby star was presented as another stepping stone toward the moment when a telescope powerful enough to read atmospheres would finally reveal what those worlds were actually like. By March 2022, just months before Webb's first science data would arrive, the total number of confirmed exoplanets crossed 5,000. NASA marked the milestone publicly. 5,000 worlds beyond our solar system, confirmed through multiple detection methods, catalogued and characterized by size, orbital period, and host star properties. The number carried enormous symbolic weight. It represented a journey from 0 known exoplanets to a vast and growing census in just 27 years. Each of those 5,000 planets was real. Each had been found through rigorous observational work and confirmed through independent analysis. The catalogue was one of the genuine achievements of modern astronomy, but the catalogue was also, in a precise and important sense, a census of silhouettes. 5,000 planets had been found. For the overwhelming majority, almost nothing was known beyond size and orbital period. A few dozen had crude atmospheric hints from Hubble or Spitzer. A handful had measured masses from radial velocity follow-up. For most of those 5,000 worlds, the catalogue entry amounted to little more than a name, a radius, an orbital period, and a rough temperature estimate. The catalogue told you what existed out there. It did not tell you what anything was like. This was the state of human knowledge about alien worlds at the moment. Webb opened its eyes. A vast ledger of detected worlds. A deeply embedded cultural narrative that treated the habitable zone as a reliable proxy for habitability and the abundance of rocky planets as evidence of Earth-like abundance. An implicit assumption carried by scientists and public alike that better instruments would progressively reveal a more inviting cosmos, that the trajectory from detection toward characterization would continue the hopeful trend, that the closer we looked, the more recognizable alien worlds would become. That assumption was about to be tested, and the test would not go the way anyone expected. Webb was not the first telescope to study exoplanet atmospheres. That distinction belongs to instruments that came before it, instruments that pushed the boundaries of what was technically possible in their era and produced results that were genuinely valuable, but that also, in ways that would only become fully apparent in retrospect, allowed imagination to fill spaces that only data should occupy. To understand why Webb changed the conversation so completely, you first need to understand what those earlier instruments could and could not do, and why the difference between them and Webb is not a matter of degree but of kind. The two most important space telescopes for exoplanet atmospheric work before Webb were the Hubble Space Telescope and the Spitzer Space Telescope. Hubble, launched in 1990, was primarily an optical and ultraviolet observatory, though it carried some near-infrared capability. Spitzer, launched in 2003, was a dedicated infrared telescope, but with a primary mirror just 85 centimeters across, roughly the diameter of a large dinner table. Both contributed genuinely to what was known about alien atmospheres. Hubble made some of the earliest detections of atmospheric signatures on exoplanets, identifying sodium in the atmosphere of the hot Jupiter HD 209458b in 2002. Spitzer mapped thermal emissions from several gas giants, producing crude information about temperature distribution on distant worlds. Together, these instruments demonstrated that exoplanet atmospheric characterization was possible in principle, not just theoretically conceivable, but actually achievable with real telescopes and real data. But both operated under constraints that limited how deeply they could probe. Hubble's infrared capability was restricted to a narrow range of wavelengths and relatively modest sensitivity. The molecular signatures that most clearly define an atmosphere, carbon dioxide, methane, water vapor, ammonia, sulfur compounds, produce their strongest and most diagnostic absorption features in the mid-infrared, a region of the electromagnetic spectrum where Hubble was largely unable to reach. Spitzer could see deeper into the infrared, but its small mirror collected far less light, which meant that its spectral measurements were noisy and imprecise. You could sometimes detect that a molecule was probably present, but you could not determine how abundant it was, at what altitude it resided, how it interacted with other chemical species, or what physical processes had produced it. The result was atmospheric characterization that resembled trying to read a page of text through frosted glass. You could tell that words existed on the page. You might catch a letter here, a fragment of a word there, but the full sentences, the meaning, the story remained smeared and unresolvable. Scientists published papers reporting tentative detections of water vapor, hints of haze, possible carbon dioxide features on various exoplanets. Those results were real achievements given the tools available. But they barely touched what atmospheric characterization genuinely requires. Consider what you actually need to know about a planet's atmosphere to determine whether it is hospitable or hostile. You need to know the chemical composition, not merely whether water exists, but in what abundance, at what pressure levels, alongside what other molecules. You need to know the temperature structure, how heat distributes from the day-facing hemisphere to the night-facing hemisphere, from the equator toward the poles, from the surface upward, through the atmospheric column. You need to know whether clouds or hazes are present, because clouds can mask underlying chemistry and fundamentally alter how energy moves through the system. You need to know whether photochemistry is occurring, whether the parent star's radiation is actively driving chemical reactions that create or destroy molecules in the upper atmosphere. You need to know whether the atmosphere is stable over geological time or actively hemorrhaging into space, stripped away by the stellar wind or driven off by radiation pressure. None of these questions could be answered with any confidence using pre-Webb instruments. The atmospheric information available for most exoplanets amounted to a handful of isolated molecular suggestions surrounded by enormous uncertainty. And yet the public narrative treated every such detection as though it were a comprehensive weather report from an alien world. James Webb was built to close that gap, not partially, decisively. Every major engineering choice in the telescope's design reflects a single overriding priority: sensitivity to faint infrared light. The primary mirror stretches 6.5 meters across, assembled from 18 hexagonal segments coated in a microscopically thin layer of gold, chosen specifically because gold reflects infrared light more efficiently than any other practical coating material. The 5-layer sunshield, roughly the size of a tennis court when fully deployed, keeps the telescope's instruments at temperatures below -230 degrees Celsius, cold enough to prevent the telescope's own thermal radiation from overwhelming the faint infrared signals it is trying to detect. The orbital position at the second Lagrange point, 1.5 million kilometers from Earth in the direction away from the Sun, keeps Webb in permanent shadow behind its sunshield while maintaining a stable thermal environment. Everything about the telescope is engineered around the single goal of detecting the faintest possible infrared signals with the lowest possible noise. This matters for exoplanet atmospheric science because the universe's chemical information is written primarily in infrared wavelengths. Molecules vibrate and rotate at frequencies corresponding to infrared light. When a molecule absorbs a photon at one of these characteristic frequencies, it removes that wavelength from the passing light, leaving a gap in the spectrum, a dark absorption feature at a specific wavelength that functions like a molecular fingerprint. different molecules produce different patterns of these features. Water vapor has its own distinctive pattern. Carbon dioxide has its own. Methane, ammonia, hydrogen sulfide, sulfur dioxide, silicates each leaves its signature in a different region of the infrared spectrum, and Webb can read those signatures with enough precision to determine not just that a molecule is present, but approximately how abundant it is and how its concentration varies through the atmospheric column. Webb carries 4 science instruments. 3 of them play central roles in exoplanet characterization. The near-infrared spectrograph, called NIRSpec, covers wavelengths from roughly 0.6 to 5.3 micrometers. The near-infrared imager and slitless spectrograph, called NIRIS, covers a similar range and includes an observing mode designed specifically for transit spectroscopy of bright nearby stars with orbiting planets. The mid-infrared instrument, called MIRI, extends coverage from 5 to 28 micrometers, opening a window into the thermal infrared, where many of the most critical molecules produce their strongest spectral features. Together, these instruments give Webb continuous spectral coverage from the red end of the visible spectrum through the deep mid-infrared, a range that encompasses the fingerprints of virtually every molecule relevant to planetary atmospheres. No previous space telescope had this combination of wavelength coverage, spectral resolution, and raw light-gathering area working together. Webb's mirror collects roughly 50 times more light than Spitzer, and approximately 6 times more than Hubble in the near-infrared. That difference is not incremental. It is the difference between hearing a whisper from across a crowded room and hearing a clear conversation from the adjacent table. Here is what most people misunderstand about how Webb studies exoplanets. When you see an artist's rendering of an alien world with swirling cloud patterns and glowing volcanic plains, that image did not come from Webb. Webb does not photograph distant planets. It cannot produce an image of an exoplanet showing what it looks like visually. The planets Webb studies are too far away and too close to their blindingly bright parent stars to be resolved as separate objects. In almost every case, the planet and its star appear as a single unresolvable point of light, even to the most powerful telescope ever built. What Webb does instead is something far more subtle and far more revealing than photography. It reads the light itself. The primary technique is called transmission spectroscopy. It works like this. When a planet transits its star, passing in front of the stellar disk from our perspective, a small fraction of the starlight passes through the thin ring of the planet's atmosphere at the edge of its disk before reaching Webb's detectors. That atmospheric annulus acts as a filter. Molecules in the atmospheric gas absorb specific wavelengths of the passing starlight. The light that arrives at Webb is therefore slightly altered. At wavelengths where atmospheric molecules absorb strongly, the planet appears fractionally larger because those layers of atmosphere are opaque and block additional starlight. At wavelengths where the atmosphere is transparent, the planet appears smaller. By measuring how the apparent size of the planet changes across hundreds or thousands of individual wavelengths, astronomers construct a transmission spectrum, a graph showing how much starlight the atmosphere absorbs as a function of wavelength. The bumps and dips in that graph correspond directly to specific molecules. A broad absorption feature centered around 1.4 micrometers indicates water vapor. A sharp dip near 4.3 micrometers signals carbon dioxide. Features near 3.3 micrometers suggest methane. Sulfur dioxide appears near 4 micrometers and again between 7 and 9 micrometers. Each molecule leaves its mark in a different part of the spectrum, and Webb can read those marks with sufficient precision to determine not just presence, but abundance. The depth and shape of each absorption feature carry additional information. A deep, broad water vapor feature, without accompanying cloud signatures, suggests a relatively clear atmosphere rich in water. A muted, flattened spectrum with weak features across all wavelengths suggests the presence of hazes or high-altitude clouds that are blocking the view of deeper atmospheric layers, absorbing and scattering light in ways that wash out the molecular signatures beneath. A spectrum showing unexpected molecular combinations, such as sulfur dioxide appearing alongside water vapor and carbon dioxide, suggests active photochemistry, a process in which the parent star's ultraviolet radiation is breaking apart stable molecules in the upper atmosphere and driving the formation of new chemical species. Transmission spectroscopy is powerful, but it has limits that matter for understanding Webb's results. It primarily probes the thin atmospheric annulus around the planet's limb, the narrow transitional region where the atmosphere shifts from opaque to transparent, as seen from our vantage point. It does not directly measure conditions at the planet's surface or deep in its lower atmosphere. It is also most effective for planets with thick, extended atmospheres, which is why hot Jupiters and sub-Neptunes have produced the richest and most information-dense transmission spectra. Small rocky planets with thin atmospheres produce much weaker signals, requiring many repeated observations stacked together to extract a planetary signature from the noise. This is where Webb's second major technique becomes critical. Emission spectroscopy works differently. Instead of measuring starlight filtered through the planet's atmosphere during transit, emission spectroscopy measures the planet's own thermal radiation. Every object warmer than absolute zero emits infrared light. When a planet passes behind its star in an event called a secondary eclipse, the combined brightness of the star and planet system drops by the amount contributed by the planet alone. By measuring the system's light immediately before the eclipse and comparing it to the light measured during the eclipse when only the star is visible, astronomers can isolate the planet's thermal emission. That emission carries its own spectral information. Molecules in the atmosphere absorb and re-emit thermal radiation at characteristic wavelengths, just as they do with transmitted starlight, but emission spectroscopy probes different atmospheric regions and provides complementary physical information. It is particularly sensitive to the planet's temperature structure, revealing how temperature varies with altitude. In some cases, it reveals thermal inversions, layers where temperature increases with altitude rather than decreasing, which can indicate the presence of specific, strongly absorbing molecules high in the atmosphere. Webb's third major technique is the phase curve observation. Instead of measuring the planet's light only during secondary eclipse, phase curves track how the planet's apparent brightness changes continuously across its entire orbit. When the planet's day side faces toward us, the system appears brightest. When the night side faces toward us, the system appears faintest. The shape of this brightness variation over a complete orbit reveals how efficiently the atmosphere transports heat from the hot illuminated hemisphere to the cool dark hemisphere. A planet with robust atmospheric circulation shows a smaller contrast between day-side and night-side brightness because winds redistribute thermal energy. A planet with little or no atmospheric circulation shows extreme contrast, one hemisphere baking under permanent stellar exposure while the other freezes in permanent darkness. Phase curves also reveal the location of the hottest point on the planet. On a tidally locked world with no atmosphere, the hottest point sits directly at the substellar point, the location on the surface facing the star. If an atmosphere with winds exists, the hottest point shifts eastward, carried by atmospheric circulation. The magnitude of this offset provides information about wind speeds and the overall dynamics of atmospheric heat transport. In late 2025, Webb produced the first three-dimensional temperature map of an exoplanet using a technique called spectroscopic eclipse mapping. By combining spectral information with spatial information encoded in precisely how a planet disappears behind its star during secondary eclipse, researchers constructed a map showing temperature variations not just across the planet's surface, but at different atmospheric altitudes simultaneously. This was not a photograph. It was a thermal portrait, assembled from the mathematical analysis of how the planet's light signature evolved during eclipse entry and exit. But the physical information it contained was more detailed and more precise than any image could convey. There is one more capability that deserves attention because it produced some of Webb's most striking early results: direct imaging. Most exoplanets are found and studied indirectly, through their gravitational influence on their star, or through the dimming they cause during transit. But a small category of planets, those that are very young, very massive, and orbiting at large distances from their host stars, emit enough infrared light to be detected separately from the star. Webb's coronagraphic instruments can block the overwhelming glare of the parent star and reveal the faint infrared glow of an orbiting planet directly, capturing its own thermal emission. This allowed Webb to study objects like VHS 1256b, a young planetary mass companion roughly 40 light-years from Earth, by collecting the planet's own light across wavelengths from 1 to 20 micrometers. The result was the most detailed spectrum ever obtained for a directly imaged exoplanet, a chemical inventory that included water vapor, methane, carbon monoxide, carbon dioxide, and silicate cloud features, all from a single target, all with unprecedented clarity. Understanding all of these techniques matters because it explains why Webb's atmospheric results carry a weight that previous detections did not. When Hubble tentatively identified water vapor on a hot Jupiter years ago, that detection rested on a single spectral feature observed with marginal statistical confidence in a narrow wavelength range. When Webb detects water vapor, it observes the molecule's absorption signature across multiple wavelength bands simultaneously with high statistical confidence, while also constraining half a dozen other molecular species, the atmospheric temperature profile, and the presence or absence of clouds. The certainty is different. The depth of information is different. The ability to distinguish between competing interpretations is categorically different. This distinction carries enormous consequences for the question at the center of this story. When Webb tells you that a planet's atmosphere contains sulfur dioxide produced by photochemistry, that conclusion rests on spectral features detected at multiple wavelengths, confirmed by independent observing modes, and consistent with photochemical models that predict exactly how that molecule forms under those stellar radiation conditions. When Webb tells you that a rocky planet's thermal emission is consistent with a bare, airless surface, that conclusion rests on precise temperature measurements compared against detailed physical models for atmospheres of various compositions and thicknesses. These are not tentative suggestions or preliminary impressions. They are robust physical measurements backed by the most sensitive infrared observatory ever placed in space. And this is precisely why Webb's findings carry such a different emotional register than everything that came before. When the data was sparse and the uncertainties were large, imagination could expand into the gaps and project whatever it wanted onto distant worlds. A marginal water vapor detection on a faraway planet could be elaborated into a story about alien oceans. A rocky planet in the habitable zone could be dressed in blue and green by an illustrator and presented as a plausible second Earth. The uncertainty was not a flaw in the public narrative. It was the space in which hope lived undisturbed. Webb collapsed that space, not by failing to find interesting things, but by finding so many specific, precise, unambiguous things that the freedom to imagine evaporated. When you know what molecules fill a planet's atmosphere, at what abundances, under what thermal conditions, you can no longer project whatever you wish onto that world. The data constrains the picture. And the picture Webb's data has consistently been painting across dozens of targets, spanning multiple planetary categories and multiple stellar environments, is not the picture anyone expected. Before we examine what that picture actually shows, there is one final aspect of Webb's capability that explains why even careful scientists were sometimes surprised by what they found. Webb's sensitivity allows it to detect atmospheric features of extraordinary faintness. The transmission spectroscopy signal from a hot Jupiter's atmosphere might dim the parent star's light by only a few hundred parts per million. For a smaller sub-Neptune, the signal might be only a few tens of parts per million. For a rocky planet the size of those in the TRAPPIST-1 system, the expected atmospheric signal amounts to just a few parts per million, comparable to detecting a firefly crawling across the face of a searchlight viewed from 100 kilometers away. To extract signals this faint, Webb must observe multiple transits of the same planet and combine the data, building up the planetary signal while averaging down the random noise. For bright nearby targets, a single transit can yield a rich spectrum. For fainter or smaller targets, astronomers must stack observations from 3, 5, sometimes 10 or more separate transit events to achieve the necessary precision. Each observation takes hours. The data reduction is painstaking and technically demanding. Systematic effects from the instrument, the detector, and the star itself must be carefully modeled and removed before the planetary signal can be isolated. This is why Webb's exoplanet results emerge gradually across months and years, rather than arriving all at once. Some of the most scientifically consequential findings, particularly the atmospheric characterization of rocky planets in habitable zones, remain works in progress, with each new transit observation adding another layer of precision to a picture that is still resolving. But even the early results, from the brightest and most tractable targets, were enough to fundamentally alter the scientific conversation. Because what Webb found on those easy targets, the hot Jupiters and warm sub-Neptunes, where atmospheric signals are clearest and strongest, established a pattern that almost no one had fully prepared for. These worlds, the first ones Webb could read in real detail, were not mysterious blank canvases waiting to receive humanity's projections. They were extreme environments, operating under physical and chemical conditions so severe and so alien that the dream of a galaxy populated by Earth-like worlds began, quietly and inexorably, to look like exactly what it had always been: a dream. The telescope was ready, the targets were selected, the data was coming, and the universe was about to begin telling us what it was actually like, on its own terms, without regard for what we had hoped to hear. 10:10. The first exoplanet atmosphere that Webb dissected in full was not supposed to be the story. It was supposed to be the test run. WASP 39b, a bloated gas giant, roughly the mass of Saturn, but puffed up to a diameter exceeding Jupiter's, orbiting a sun-like star approximately 700 light-years from Earth, was selected as one of Webb's early release science targets for a straightforward reason. It was easy. Its atmosphere was thick and extended, its host star was bright enough to produce strong signals, and its orbital period was short enough that multiple transits could be observed in a reasonable amount of telescope time. The planet was not a candidate for habitability. Nobody imagined life flourishing on a world with an atmospheric temperature of roughly 870 degrees Celsius. It was chosen as a proving ground, a calibration exercise, a demonstration that Webb's atmospheric characterization pipeline worked as intended before the telescope turned toward more scientifically delicate targets. What the data revealed went far beyond calibration. 5 independent research teams from the Transiting Exoplanet Early Release Science Program trained different Webb instruments on the planet during transit and combined their results into the most complete chemical portrait of an alien atmosphere ever assembled. The spectrum that emerged was not merely clear, it was dense with information, every wavelength range yielding new molecular detections, new constraints on atmospheric structure, new evidence of processes that had never been observed on any planet outside our solar system. Webb detected sodium, potassium, water vapor, carbon dioxide, carbon monoxide, and patchy clouds scattered throughout the atmospheric column. Each molecule appeared clearly across multiple wavelength bands, confirming detections that Hubble had only suggested with marginal confidence. Where previous instruments had produced blurred, ambiguous spectral features for this same planet, Webb delivered sharp, unambiguous molecular signatures with statistical confidence levels that left no room for interpretation. But the detection that mattered most was one that no previous telescope had ever found on any exoplanet: sulfur dioxide. Sulfur dioxide does not form easily under the equilibrium chemical conditions expected deep in WASP 39b's atmosphere. At the temperatures and pressures prevailing in its lower atmospheric layers, sulfur should exist primarily as hydrogen sulfide. For sulfur dioxide to appear in detectable quantities, something must be actively breaking apart hydrogen sulfide and water molecules and recombining their constituent atoms into new configurations. That something is ultraviolet radiation streaming from the parent star. High-energy photons penetrate the upper atmosphere, disrupt stable molecular bonds, and trigger a cascade of chemical reactions that produce sulfur dioxide as a byproduct. This process is called photochemistry, and WASP 39b provided the first definitive evidence that it operates in exoplanet atmospheres. The significance of this finding extended well beyond the specific chemistry of one hot gas giant. photochemistry is not a gentle background process. It means the atmosphere is being actively rewritten in real time by its star's radiation field. The chemical composition you observe is not simply the equilibrium product of temperature and pressure. It is the result of a violent, continuous interaction between the planet's atmospheric gases and the high-energy photons raining down from above. The star is reaching into the atmosphere and rearranging its molecular architecture at every moment. On Earth, ultraviolet radiation drives the photochemical reactions that create the ozone layer, splitting oxygen molecules that then recombine into ozone. The process is essential for life, shielding the surface from the same radiation that drives it. But on WASP 39b, the equivalent process produces sulfur compounds in a hydrogen-dominated atmosphere heated to temperatures that would incinerate any terrestrial organism in an instant. The chemistry is exotic, the environment is savage, and the most important implication was this: if photochemistry reshapes the atmospheres of hot gas giants this dramatically, it almost certainly reshapes the atmospheres of every planet exposed to significant stellar ultraviolet radiation, including smaller, potentially habitable worlds orbiting active stars. WASP 39b was the opening statement of a much longer and much harsher argument. What followed was an accumulating body of evidence that reinforced the same pattern with increasing severity. In late 2025, a team of researchers published the first three-dimensional temperature map of an exoplanet using Webb's spectroscopic eclipse mapping technique. The target was WASP 18b, an ultra-hot Jupiter roughly 10 times the mass of Jupiter, orbiting a star approximately 400 light-years away in the constellation Phoenix. This planet completes a full orbit in less than 23 hours, racing around its star so tightly that its dayside atmosphere reaches temperatures exceeding 2,300 degrees Celsius. At those temperatures, atmospheric chemistry enters a regime that has no parallel anywhere in the solar system we inhabit. Water molecules, among the most chemically stable and common molecules in the universe, cannot survive. The thermal energy at WASP 18b's dayside is sufficient to break the bonds holding hydrogen and oxygen together, dissociating water vapor into its individual atomic components. This is not a subtle chemical shift. It is not evaporation or phase change or any process with an analog in terrestrial experience. It is the wholesale unmaking of a molecule that persists inside volcanic hydrothermal vents on Earth, inside superheated deep-sea systems where temperatures and pressures would destroy most other compounds. Water is one of the most thermally resilient common molecules in the universe. On WASP 18b's dayside, the temperature exceeds even water's tolerance. The bonds snap, the molecule ceases to exist. And this molecular destruction does not occur in a localized region. Webb's temperature map showed that dissociation operates across a substantial fraction of the dayside atmosphere, creating a gradient where water vapor persists in cooler peripheral regions and is torn apart as conditions grow more extreme, approaching the substellar point directly beneath the star. The map also showed that the hottest region on the planet was shifted slightly eastward of the substellar point, indicating that powerful atmospheric winds were carrying superheated gas around the limb of the planet before it could radiate all its energy back into space. But those winds could not redistribute heat evenly. The night side remained dramatically cooler, producing temperature contrasts of hundreds of degrees between hemispheres. The three-dimensional nature of the map added a vertical dimension to this picture. Temperature varied not only across the planet's surface, but upward through the atmospheric column, creating stratified layers where different chemical processes dominated at different altitudes. The atmosphere was not a uniform envelope. It was a structured, dynamic system operating under conditions so extreme that the chemistry changed fundamentally depending on where within it you sampled. WASP 18b is a world where the concept of weather requires complete redefinition. Winds carrying dissociated atoms howl across a dayside glowing at temperatures exceeding the surfaces of many stars, while the night side simmers at conditions that would merely melt steel by comparison. The three-dimensional thermal portrait Webb assembled was not just scientifically impressive, It was a visceral demonstration that alien planets are not places that yield to familiar analogies. They operate under physical regimes where the most chemically stable molecules in the universe are unmade by sheer heat. Then came WASP 121b, and the picture grew more disturbing still. WASP 121b, also known by its approved name Tylos, is an ultra-hot Jupiter orbiting an F-type star approximately 850 light-years from Earth in the constellation Puppis. It completes an orbit in just 1.275 Earth days, locked in a blistering gravitational embrace with its parent star. Its dayside temperature exceeds 2,300 degrees Celsius, placing it firmly in the category of worlds where atmospheric chemistry operates in an entirely different mode than anything in our solar system. In late 2025, a team using Webb's NIRISS instrument observed the planet continuously for approximately 37 hours, capturing its complete orbital phase curve, watching it transit the star, sweep around through its orbit, and pass behind the stellar disk in secondary eclipse. The picture that emerged from that continuous monitoring was extraordinary and deeply unsettling. WASP 121b is not merely a hot planet, it is a dying one. The planet is actively losing its atmosphere. Intense stellar radiation heats its uppermost atmospheric layers so severely that light elements, particularly helium, reach escape velocity and stream away from the planet in vast continuous outflows. Previous ground-based observations had detected hints of atmospheric escape during individual transit events. Webb's continuous monitoring revealed something far more complex and dramatic than a simple atmospheric leak. The planet is enveloped in two enormous tails of escaping helium, structures so large they had not been anticipated even by researchers who had already suspected atmospheric loss was occurring. One tail streams behind the planet in its orbit, pushed backward by radiation pressure and the stellar wind, stretching across space like a comet's wake made of planetary atmosphere. The second tail, rarer and more difficult to explain, extends ahead of the planet in its orbital path, curving forward toward the star, likely drawn by the star's gravitational influence on the escaping material. Together, these twin helium tails span nearly 60% of the planet's entire orbital circumference. The planet is hemorrhaging its atmosphere across a vast region of its own star system, leaving a continuous trail of escaped gas that traces the arc of its orbit like the remnant of something being consumed. The researchers described the complexity of the outflow as far exceeding their prior expectations, revealing interactions between the escaping atmosphere, the stellar wind, and the star's gravitational field that current theoretical models struggle to fully reproduce. WASP 121b is a planet in the active process of being unmade by the same star it orbits. The atmospheric mass that defines it as a gas giant is being continuously stripped away, molecule by molecule, atom by atom, carried off into space in structures that dwarf the planet itself. This is not a stable environment with a persistent atmosphere. It is a transient object, a world whose current state is a snapshot in a process of slow destruction that will eventually alter what the planet fundamentally is. Atmospheric escape is not limited to this one extreme example. Webb has observed helium outflows on multiple targets, including the sub-Neptune WASP 107b, a so-called superpuff planet whose density is so anomalously low that its atmosphere must be enormously inflated relative to its mass. Webb's observations revealed dramatic helium streams pouring from this world as well, confirming that atmospheric escape is a widespread process, operating across a range of planetary masses and compositions. Planets do not simply form and persist unchanged. They are continuously sculpted by their stellar environments, often violently, often in ways that progressively strip away the very atmospheric envelopes that might otherwise make them chemically interesting. Even planets that might seem less extreme, more familiar in their basic parameters, turned out to harbor surprises that defied existing models. Epsilon Indi AB is a cold gas giant orbiting a star system just 12 light-years from Earth, making it one of the nearest exoplanets ever studied by direct imaging. It is several times the mass of Jupiter and sits at a wide orbital separation from its host star, the kind of configuration that should produce a relatively comprehensible atmosphere governed by the same physical principles that have been used to model the cold gas giants of our own solar system for decades. Jupiter and Saturn have been studied intensively for generations. Their atmospheric chemistry at low temperatures, the layers of ammonia and water, ice clouds, the methane and hydrogen dynamics had become a framework that researchers expected to apply, with adjustments, to cold giant exoplanets found elsewhere. Webb looked at Epsilon Indiab and found something that did not fit that framework. The data revealed unexpected water ice clouds in the planet's atmosphere, thick and patchy formations that standard atmospheric models had not predicted at this scale. More puzzling still, ammonia, which should have been clearly detectable according to those same models, was either absent or so heavily suppressed beneath the unexpected cloud layers that it produced no identifiable spectral signature. The mismatch between theoretical prediction and direct observation was significant enough to require a reassessment of the underlying atmospheric models. Here was a planet sitting in the nearest star system, accessible to Webb's direct imaging capability, a cold, massive world in a wide orbit, the closest analog to a familiar giant planet that the observable neighborhood could offer. And even this supposedly approachable world operated on its own terms, shaped by a formation history and atmospheric dynamics that our existing models had not adequately anticipated. This result carries an implication that reaches beyond the specific chemistry of one nearby gas giant. It demonstrates that Webb's confrontations with alien complexity are not confined to the most extreme cases, not restricted to scorched hot Jupiters and tidally locked close-in planets, where conditions are obviously unlike anything in our experience. Even in the category of exoplanet most closely resembling objects we thought we already understood, cold giant planets, at comfortable orbital distances around nearby stars, direct observation reveals an atmosphere that does not behave as predicted. If the gap between expectation and physical reality exists in this most familiar of planetary categories, it exists everywhere. And then there is VHS 1256b, a young planetary mass object approximately 40 light-years from Earth, orbiting two small stars in a wide arc that takes it hundreds of years to complete a single circuit. Webb produced the most detailed infrared spectrum ever obtained for a directly imaged exoplanet by collecting this object's own light across wavelengths from 1 to 20 micrometers, constructing a chemical portrait that included water vapor, methane, carbon monoxide, carbon dioxide, sodium, and potassium, all from a single target, all with a clarity that no previous instrument had approached. But the detection that most vividly illustrated the strangeness of alien atmospheres was the signature of silicate particles suspended in the upper atmosphere in vast, churning cloud formations. These are not clouds in any sense that carries terrestrial meaning. They are not condensed water vapor or ice crystals or any material that produces clouds on Earth. They are clouds of hot sand, silicate particles, essentially microscopic grains of pulverized rock, condense from the gaseous phase in the upper atmosphere at temperatures approaching 800 degrees Celsius and form thick, dynamic cloud layers that swirl and churn across the planet's face. The planet's brightness varies by as much as 25% as these silicate clouds rotate in and out of view during its 22-hour day, making it the most photometrically variable planetary mass object ever measured. The weather on this world is not meteorology in any sense the word was invented to describe. It is geological violence, suspended in an atmosphere, rock raining upward from hot gas before falling back again, an endless cycling of pulverized mineral material through a sky that glows at temperatures capable of melting aluminum. A subsequent study of VHS 1256b's atmospheric dynamics added another layer of unexpected complexity. Scientists had assumed that a planet of this mass would exhibit circulation patterns broadly similar to Jupiter's organized banded structure, with alternating wind streams flowing in opposing directions around the planet. producing the familiar striped appearance of our solar system's largest gas giant. Instead, the observational data indicated that VHS 1256b's atmosphere is dominated by enormous planetary-scale waves and chaotic turbulent mixing rather than orderly banded circulation. The atmospheric dynamics are fundamentally different from Jupiter's. Not a scaled version of a familiar regime, but a genuinely distinct mode of operation governed by different physical balances, producing different outcomes. Even the assumption that giant planets should have Jupiter-like atmospheres turns out to be wrong when you actually measure them. Each of these findings is remarkable in isolation. Together, they form the opening chapters of a story that the data is telling consistently and without qualification. Alien worlds are not places that yield to familiar frameworks. The first wave of planetary atmospheres Webb examined in detail revealed environments dominated by photochemical violence, thermal extremes capable of destroying the most stable molecules in the universe, atmospheric hemorrhaging on scales that dwarf the planets experiencing it, cloud systems made of condensed rock, and atmospheric dynamics that defy the models built from our own solar system's examples. And these were the easy targets, the ones bright enough and large enough to produce the clearest signals, the ones where Webb's capabilities were least constrained by noise and stellar interference. If the easiest planets in the catalogue turned out to be this harsh and this strange, the question that followed was inescapable. What would the harder targets reveal? The smaller worlds, the rocky worlds, the ones sitting in habitable zones, the ones that had anchored the optimistic narrative for 2 decades, the ones everyone most desperately wanted to understand. Webb was already turning its instruments toward those targets. The data was accumulating, and the answer it was assembling was not the one the dream had promised. The Trappist, one system was supposed to be the answer, not a partial answer, not a promising lead requiring decades of additional investigation before yielding anything definitive. The answer, the place where the dream of nearby habitable worlds would be confirmed or refuted, with enough clarity that the question of whether Earth-like conditions existed beyond our solar system would finally have real observational data to rest on, rather than statistical extrapolation and hopeful inference. The system's credentials were extraordinary. Trappist 1 is an ultra-cool red dwarf star, a dim and ancient ember of stellar fusion, roughly 40 light-years from Earth in the constellation Aquarius. 40 light-years is an almost incomprehensible distance by any human standard of measurement. Light itself, traveling at just under 300,000 kilometers per second, takes 40 years to cross that gulf. And yet in the context of a galaxy spanning 100,000 light-years, 40 light-years is practically next door. Trappist 1 is among the nearest stars accessible to Webb's atmospheric characterization capabilities. It sits in our immediate cosmic neighborhood. Orbiting this dim star are 7 rocky planets, all of them approximately Earth-sized, all of them packed into orbital configurations so compact that the entire system would fit comfortably within the orbit of Mercury around our own Sun. 3 of these planets, designated E, F, and G, orbit within the star's habitable zone, receiving roughly the right amount of stellar energy for liquid water to persist on their surfaces under favorable atmospheric conditions. The system had been studied intensively since its discovery in 2017. Researchers had measured the planet's sizes, masses, densities, and orbital parameters with remarkable precision. The density measurements confirmed that several of the planets had compositions consistent with rocky, potentially water-bearing interiors. Theoretical models suggested that some of them might have retained substantial atmospheres capable of moderating surface temperatures. The Trappist 1 system was, in almost every respect, the ideal target. 7 rocky planets, 3 in the habitable zone, orbiting a nearby star accessible to Webb's instruments. If Earth-like conditions existed anywhere that humanity could study with current technology, the consensus pointed here. And Webb had the tools to look. The telescope began observing the system early in its science mission, targeting the innermost planets first. Trappist 1b, the closest planet to the star, was observed in secondary eclipse using MIRI at a wavelength of 15 micrometers. The measurement was designed to determine whether the planet possessed a substantial atmosphere by comparing its observed dayside temperature to theoretical predictions for two contrasting scenarios. A planet with a thick atmosphere would redistribute heat from its permanently sunlit dayside to its permanently dark nightside, producing a dayside temperature measurably lower than what a bare rock would achieve. A planet without an atmosphere would absorb all the stellar energy falling on its dayside and radiate it directly back into space from that same hemisphere, producing a higher dayside temperature with no thermal buffering from atmospheric circulation. The measurement did not require detecting individual molecular absorption features. It simply compared an observed temperature to a physically predicted temperature. The question was binary. Does this planet have a thick atmosphere or not? The result, published in 2023, indicated that TRAPPIST-1b's thermal emission was consistent with a dark, bare, rocky surface with little or no substantial atmosphere. The measured dayside temperature matched the prediction for a world directly absorbing and re-emitting stellar radiation without any atmospheric mediation. No thick carbon dioxide layer, no substantial nitrogen envelope, no dense atmospheric blanket of any composition that the measurement could detect. Let that finding settle for a moment before moving past it. This is a planet roughly the same size as Earth. It is composed of rocky material with a density suggesting a composition broadly similar to our own world. It orbits a star in a compact system that had been studied, modeled, and written about more extensively than almost any other planetary system beyond our own. It was one of the first rocky exoplanets Webb examined in meaningful detail, and the first detailed look suggested a world that had been stripped bare. Whatever atmosphere TRAPPIST-1b may once have possessed, whether a thick primordial hydrogen envelope or a thinner layer of gases released by volcanic activity over billions of years, appears to be gone. The star, dim and cool as it is by the standards of stellar objects, had evidently subjected this planet to enough cumulative radiation over the billions of years of its existence to leave behind an airless rock. TRAPPIST-1c followed, more MIRI eclipse observations, a similar result. The thermal emission from the second planet was again consistent with a bare or nearly bare surface, disfavoring atmospheric models that would have produced a meaningfully lower dayside temperature through heat redistribution. In April 2026, a comprehensive analysis of Webb thermal phase curves for both TRAPPIST-1b and TRAPPIST-1c was published in Nature Astronomy, confirming that both innermost planets emit thermal radiation consistent with bare rocky surfaces, strongly disfavoring atmospheric models with surface pressures above approximately 1 bar. The paper noted that these results suggest divergent evolutionary pathways or atmospheric loss processes, a careful scientific way of saying that two Earth-sized rocky worlds orbiting in the same system appear to have lost whatever atmospheres they once had through processes that the system's stellar environment almost certainly drove. Two Earth-sized rocky planets, stripped of any thick protective atmosphere, orbiting the most scrutinized potentially habitable system in all of exoplanet science. The results for the outer, more potentially habitable TRAPPIST-1 planets have been harder to obtain and far more ambiguous in what they reveal. TRAPPIST-1e, the planet most consistently cited in scientific discussions as the system's best candidate for habitability, was observed with Webb's near-spec instrument in transmission spectroscopy over multiple transit events. The results, published in 2025, were frustrating in the specific way that only data can be frustrating when it refuses to deliver a clean answer in either direction. The transmission spectrum showed significant contamination from the host star itself. Red dwarf stars like TRAPPIST-1 have magnetically active, structurally complex surfaces populated by dark star spots and bright regions called faculae. When a planet transits such a star, the starlight that passes through the planet's atmosphere also carries the imprint of whatever surface features the planet crossed in front of or passed near. These stellar surface variations can introduce spurious spectral features into the transmission spectrum that mimic or mask genuine atmospheric signals. Separating the real planetary atmosphere from the stellar surface noise requires detailed models of the star's own surface activity, and those models carry their own substantial uncertainties. The research team found that after careful analysis, the data did not clearly favor either the presence or the absence of an atmosphere on TRAPPIST. 1e, thick hydrogen-rich envelopes were ruled out. Venus-like and Mars-like atmospheric compositions were disfavored, but thin nitrogen-dominated atmospheres with traces of carbon dioxide, the category of atmosphere most relevant to habitability discussions, remained permitted by the data. The stellar contamination was operating at precisely the level where the measurement needed to be most precise. The star's own surface activity was drowning out the signal the telescope was trying to detect, at exactly the amplitude where the presence or absence of a thin, habitable atmosphere would make itself known. After years of accumulated observations and exhaustive analysis by multiple independent research teams, the question of whether TRAPPIST, 1e, has a meaningful atmosphere remains unresolved. The answer is not no, but it is not yes. It is a silence where a signal was desperately needed, and silence, in this context, does not mean absence of data. It means the universe declining to confirm what was hoped. The deeper problem illuminated by TRAPPIST, one extends beyond any individual planet in the system. It is a structural problem with the entire category of planetary targets that had been most central to optimistic habitability estimates. Red dwarf stars, the M-dwarfs that constitute roughly 75% of all stars in the Milky Way, were long considered the most promising hunting grounds for habitable worlds, precisely because of their abundance. If even a small percentage of M-dwarf planets were habitable, the sheer numerical dominance of these stars in the galactic census would translate into billions of habitable worlds distributed throughout the galaxy. This reasoning drove much of the optimism embedded in habitability statistics. It motivated the intense focus on systems like TRAPPIST. 1. It shaped observation strategies and funding justifications across the field. But the combination of factors that defines the M-dwarf environment turns out to be consistently hostile to atmospheric retention in ways that the optimistic projections underweighted. Red dwarf stars are small and cool, but they are also magnetically active, particularly during the first several billion years of their lives, a youthful phase that lasts far longer than the equivalent active period of sun-like stars. During this extended active youth, M-dwarfs produce intense flares of ultraviolet and X-ray radiation that bombard any nearby planets with high-energy photons and charged particles. These energetic inputs heat the upper atmospheric layers of orbiting planets, driving molecules to escape velocities and eroding the atmospheric envelope from above. Simultaneously, the stellar wind, the continuous outflow of charged particles from the star's surface, strips atmospheric material from planets lacking strong enough magnetic fields to deflect it. Over billions of years, these combined processes can systematically remove whatever atmosphere a rocky planet accumulated through volcanic outgassing or primordial retention, regardless of how much atmosphere the planet started with. The planets that sit in M-dwarf habitable zones are, by geometric necessity, close to their stars. A red dwarf emits far less energy than a sun-like star, so the habitable zone sits much closer in. This proximity means that habitable zone M-dwarf planets receive more intense ultraviolet and particle radiation than a planet like Earth receives from our Sun, despite their stars being cooler. It also means they are almost certainly tidally locked, with one hemisphere permanently facing the star and the other permanently facing away, a configuration that creates extreme atmospheric circulation challenges and exacerbates atmospheric escape on the perpetually illuminated dayside. The emerging observational picture from Webb and from the broader landscape of M-dwarf exoplanet research is consistent with this physical argument. The inner TRAPPIST, one planets appear stripped. Multiple other rocky planets observed around M-dwarf stars, across the growing sample that Webb and other telescopes have examined, show results favoring bare rock interpretations. The trend is coherent across multiple stellar environments and multiple planetary targets. The closer a rocky planet orbits to an M-dwarf star, the less likely it appears to retain the kind of substantial protective atmosphere that habitability, as we understand it, requires. The habitable zone around red dwarf stars, which had been the centerpiece of the most optimistic habitability estimates because M-dwarfs are so numerous, now faces a fundamental credibility problem rooted in observational evidence rather than theoretical concern. A planet can occupy the habitable zone and still have no atmosphere whatsoever, in which case the habitable zone designation, however geometrically accurate, is physically meaningless for the question of whether life could exist on that world's surface. Then there is K2-18b, and the cautionary tale it provides about how even the most exciting Webb results can dissolve under the pressure of independent scrutiny. K2-18b is a sub-Neptune, a planet roughly 8.5 times Earth's mass, orbiting a red dwarf star, approximately 124 light-years from Earth. It sits within its star's habitable zone, and its size places it in the category of planets called sub-Neptunes, worlds between Earth and Neptune in diameter that have no equivalent in our own solar system and whose internal structures and atmospheric natures remain among the least well understood in all of exoplanet science. In 2023, a team using Webb's NIRSpec instrument reported the detection of methane and carbon dioxide in K2-18b's atmosphere, a chemical combination they argued was consistent with a theoretical planet type called a Hycean world, a planet hosting a global liquid water ocean beneath a hydrogen-rich atmospheric envelope. They also reported a tentative, low-confidence hint of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by marine biological organisms as a metabolic byproduct. The announcement generated a wave of excitement that spread far beyond the scientific community. Headlines declared that Webb had detected a potential biosignature on an alien world. The Hycean interpretation, if it could be sustained, would represent one of the most consequential discoveries in the history of astronomy. A planet with a global ocean sitting in a habitable zone, with a possible chemical fingerprint of biology. The story was irresistible. It moved through media coverage with the speed of something people desperately wanted to be true. The scientific community's response was considerably more measured, and the subsequent months illustrated with unusual clarity why caution in interpreting atmospheric data is not timidity, but necessity. In April 2025, the same research team published additional observations using Webb's MIRI instrument at mid-infrared wavelengths. They reported new evidence for dimethyl sulfide, or a chemically related compound, at roughly 3 sigma statistical confidence. 3 sigma means the signal is unlikely to be random noise alone, but it does not meet the conventional 5 sigma threshold that the scientific community requires before treating a detection as confirmed. The claim rested on spectral features in a wavelength range where instrumental systematic effects are particularly difficult to control and where multiple other molecules produce overlapping signatures that are hard to disentangle. Within months, independent analyses from multiple research groups challenged the finding. A NASA reanalysis confirmed K2-18b's water-rich atmospheric character and acknowledged the planet's chemical complexity, but found no conclusive evidence for dimethyl sulfide. A team from the University of Chicago argued that the available data was insufficiently precise to support the biosignature claim, and that the spectral features attributed to dimethyl sulfide could be equally well explained by other molecules or by residual instrumental artifacts that had not been fully removed in the original analysis. A separate study published in Astronomy and Astrophysics concluded that when all available Webb data from multiple instruments was analyzed jointly rather than piecemeal, the evidence for dimethyl sulfide was insufficient to constitute a detection. One research group noted that roughly 87% of their statistical retrievals using their preferred analytical framework returned no support for the claimed detection at all. Beyond the biosignature dispute, the Hycean world interpretation itself turned out to be far from the only physically plausible explanation for K2-18b's atmospheric composition. Alternative models proposed that the planet could be a gas-rich mini-Neptune with no surface ocean whatsoever, its interior a dense high-pressure fluid rather than a layered structure with a habitable liquid surface. Other models suggested a global magma ocean beneath a thick atmospheric envelope, a scenario that one researcher described as about as inhospitable as conditions can be. The identical atmospheric data that one team interpreted as evidence of a potentially life-bearing ocean world proved equally consistent, under different but equally defensible modeling assumptions, with a molten interior wrapped in dense gas. The same molecules, the same spectral features, the same Webb observations, pointing simultaneously toward a possible ocean and toward a possible hellscape, with no way yet to determine which interpretation was correct. K2-18b is not evidence that Webb found life. It is evidence that the gap between detecting molecules in a planetary atmosphere and determining what kind of world that planet actually is remains enormous, and that the human desire to find life can lead to premature conclusions that more rigorous and more independent analysis subsequently fails to support. The planet's atmospheric chemistry is genuinely complex and scientifically interesting. It warrants continued observation with Webb and with future instruments. But as of the most current analyses, there is no statistically robust evidence for biosignatures on K2-18b and the fundamental nature of the planet itself, whether it has an ocean, a magma surface, or something with no analog in our experience, remains unresolved. This uncertainty is itself part of the harsh truth Webb has been delivering. Even for a relatively bright, nearby, well-observed target like K2-18b, even after years of accumulated observations and exhaustive analysis by multiple independent teams, determining what a planet is actually like turns out to be far harder than the narrative of discovery made it appear. The data is real and valuable, but interpretations diverge, models compete, systematic effects persist, and the clean story of confirmed discovery that public expectations demand does not match the messy, contested, iterative reality of atmospheric science at the frontier of what is currently measurable. Away from the habitability question entirely, Webb continued revealing alien worlds of a strangeness that underlined the same basic message. In early 2026, a research team reported that Webb had detected what appeared to be an atmosphere clinging to the ancient, scorching lava planet TOI 561b. This small world orbits one of the oldest, most metal-poor stars known, circling so closely that it completes a full year in less than a single Earth day. By every conventional expectation, this planet should be completely airless. Its surface is a molten sea of magma, baked and rebaked by billions of years of intense stellar proximity. The detection of an atmosphere, if confirmed through ongoing observations, suggests that volcanic outgassing from the churning magma ocean may be continuously replenishing atmospheric gas, even as stellar radiation strips it away from above. Consider what that actually means. This is not a planet with a stable, protective envelope of gas surrounding a solid surface. It is a planet trapped in an endless cycle of atmospheric creation and destruction, a geological engine continuously producing gas from its molten interior, while the radiation field of its star simultaneously tears that gas away into space. The atmosphere does not accumulate. It does not stabilize. It does not develop the kind of persistent, chemically complex structure that could moderate surface temperatures or shield against radiation or provide the stable physical environment that anything resembling life would require. It is an atmosphere in the most minimal technical sense, a thin, transient skin of gas clinging to a world that produces air on a timescale comparable to the timescale on which the star destroys it. The planet breathes, in a manner of speaking, but every breath is stripped from it before it can do anything useful. TOI 561b has existed in this state of perpetual atmospheric emergency for longer than our entire solar system has been alive. Billions of years of magma churning, gases escaping, radiation stripping, more magma churning, an endless cycle of geological effort producing nothing that persists. The researchers described the world as a wet lava ball, a phrase that sounds almost fanciful, until you understand that it describes a surface of molten rock continuously exhaling gases into an atmosphere that is being simultaneously unmade by the same star it orbits. The existence of an atmosphere on TOI 561b, if confirmed, does not make it habitable. It makes it an illustration of the most important conceptual lesson that Webb's first years of exoplanet science have been delivering. Having an atmosphere and having a useful atmosphere are not the same thing. The gap between those two conditions can be as consequential as the gap between having an atmosphere and having no atmosphere at all. An atmosphere in a state of continuous destruction and regeneration driven by volcanic violence and stellar radiation is not an atmosphere that provides anything life requires. It is simply evidence that a geological process is occurring rapidly enough to stay ahead of the destruction, at least temporarily, at least partially, at least enough to leave a detectable trace in Webb's instruments. Each of these findings, taken in sequence, adds weight to a pattern that was becoming impossible to interpret as coincidence or observational bias. Across the most scientifically compelling targets in the exoplanet catalogue, across the rocky worlds that had anchored the optimistic habitability narrative for 2 decades, across the systems that Webb's instruments were specifically designed and specifically pointed to examine in detail, the results were consistently describing a universe less friendly to life than the dream had promised. The innermost TRAPPIST, one planet's bare, the most scientifically promising TRAPPIST, one habitable zone planet, unresolved after years of effort against a wall of stellar noise. The planet where a possible biosignature was claimed, the subject of a fierce and ongoing scientific dispute with independent teams finding the evidence insufficient. A lava world with an atmosphere caught in perpetual self-destruction. A category of star, the red dwarf, that constitutes 3/4 of all stars in the galaxy, now appearing systematically hostile to atmospheric retention on its rocky habitable zone planets. The story that the data was telling had not yet reached its final chapter, but the direction of its argument was unmistakable, and its implications reached far beyond atmospheric chemistry or stellar activity, or any of the individual physical processes Webb had been measuring. They reached into the deepest questions about what the universe is actually like, and what humanity's place within it genuinely amounts to. That reckoning deserved its own examination, and Webb's data had made it unavoidable. There is a moment in every scientific revolution when the evidence stops being a collection of individual findings and starts becoming a worldview. Individual results can be debated, qualified, contextualized, explained away with sufficient ingenuity. A single rocky planet with no detected atmosphere can be attributed to unusual formation history. A single biosignature claim that fails independent scrutiny can be filed under premature announcement and forgotten. A single system where habitable zone planets appear stripped bare can be dismissed as an unfortunate special case. An active star with an unusually aggressive radiation environment, an outlier that tells us nothing general about the broader population of worlds. Individual results leave room for the optimistic narrative to survive, patched and amended but fundamentally intact. But when dozens of independent results arrive from different instruments, different research teams, different planetary targets, different stellar environments, and different observational techniques, and when all of them consistently point in the same direction, something larger is happening. The evidence is no longer telling you about this planet or that atmosphere. It is telling you about the universe. Webb's exoplanet observations have reached that threshold. Lay the individual findings end to end. Sulfur dioxide produced by photochemical violence on WASP 39b, molecular dissociation across the day side of WASP 18b, twin helium tails hemorrhaging into space from WASP 121b. Bare rock surfaces consistent with atmospheric stripping on the 2 innermost TRAPPIST-1 planets. Sand clouds churning through the atmosphere of VHS 1256b. A contested biosignature claim on K2-18b that independent analysis after independent analysis has found insufficient evidence to support. Unexpected atmospheric complexity defying existing models on the nearest cold gas giant Webb could directly image. A lava world with an atmosphere perpetually created and perpetually destroyed. Each of these findings is significant on its own scientific terms. Together, their collective weight carries a message that transcends any single discovery. The message is this: the more directly and precisely we observe alien worlds, the less they resemble the mental images that decades of hopeful speculation constructed. The universe is full of planets. They are simply not the planets we wanted them to be. This realization does not arrive as a single dramatic announcement. It accumulates quietly, spectrum by spectrum, eclipse measurement by eclipse measurement, in the steady accumulation of data that replaces imagination with physics, and the physics consistently describes environments of extraordinary severity. Not lifeless necessarily, not permanently beyond the reach of biology in every conceivable form, but severe in ways that the popular narrative of exoplanet discovery never adequately prepared anyone to confront. To understand why this matters so deeply, you need to understand what the pre-Webb narrative actually promised. It was not an explicit promise. No serious scientist ever stated it in those exact terms. But the cumulative effect of 2 decades of exoplanet headlines, artist renderings, documentary speculations, and statistical extrapolations created an implicit understanding in the public mind that went roughly like this. The galaxy is full of rocky planets in habitable zones. At least some of them probably look and feel broadly like Earth. Blue skies, liquid water, breathable air, maybe not identical to Earth, but recognizable, relatable. Places a human being could conceptually inhabit, even if physically traveling to them remained impossible. Places that would feel, in some essential way, like somewhere rather than nowhere. This understanding was never supported by evidence. It was supported by the absence of evidence. When you do not know what a planet's atmosphere contains, you can imagine it contains anything. When you cannot measure a planet's surface temperature to within several hundred degrees, you can picture a temperate afternoon. When you have no way to determine whether a planet has clouds of water vapor or clouds of vaporized silicate rock, your mind defaults to the familiar. The unknown was not threatening. It was accommodating. It accepted whatever projection you placed upon it and reflected back a universe that looked, in broad outline, like home. Webb's data replaced the unknown with the known, and the known turned out to be alien in the deepest sense of the word. Not alien as in slightly unusual. Alien as in operating under physical regimes that share almost no common ground with terrestrial experience. Temperatures that unmake molecules, chemistry driven by stellar radiation into configurations that have no analog anywhere on Earth, atmospheres escaping into space in structures larger than the planets losing them, rocky worlds baked bare by billions of years of stellar bombardment, and in the most favorable cases, data so contaminated by stellar interference that years of accumulated observations have not yielded a definitive answer about whether a planet has any atmosphere at all. The emotional weight of this shift is subtle but profound. Human beings navigate reality through narratives, and the narrative of exoplanet discovery was among the most compelling stories of the early 21st century. It was a story of cosmic abundance and inevitable companionship. We are not alone. There are billions of worlds out there. Some of them must be like ours. The story offered a cure for cosmic loneliness, not through direct evidence of alien life, but through the sheer arithmetic improbability that all those billions of worlds could be lifeless. Webb did not disprove this story. It complicated it in ways that are more difficult to process than simple disproof would have been. The billions of worlds still exist. The habitable zones still contain rocky planets. The statistical arguments for life elsewhere in the galaxy remain mathematically coherent. What changed is the texture of the story. The narrative of easy abundance, of a galaxy scattered with Earth-like oases waiting to be confirmed, has been replaced by a narrative of conditional rarity, a galaxy full of planets, where the conditions for familiarity turn out to require a far more specific and far more fragile combination of circumstances than orbital distance alone can provide. Consider what it actually takes for a rocky planet to maintain the conditions that human intuition associates with habitability. The planet needs an atmosphere substantial enough to maintain surface pressure, sufficient to prevent liquid water from boiling directly into space. That atmosphere needs greenhouse gases in the right concentrations to keep surface temperatures within the liquid water range, but not so abundant that a runaway greenhouse effect drives temperatures to levels that destroy the very water the greenhouse gases are supposed to preserve. The atmosphere needs to remain chemically stable over geological timescales, resisting photochemical destruction by the parent star's ultraviolet output. The planet needs a magnetic field strong enough to deflect the stellar wind and prevent charged particles from sputtering away the upper atmosphere over billions of years. The parent star needs to be stable enough that its radiation output does not vary wildly, periodically sterilizing the surface with flare events energetic enough to strip atmospheric layers or irradiate any exposed biology. The planet's orbit needs to remain stable against gravitational perturbations from neighboring worlds. The planet needs sufficient geological activity to cycle carbon through its interior and regulate atmospheric composition over long timescales, but not so much activity that volcanic events continuously destabilize surface conditions. Each of these requirements eliminates a fraction of the candidate worlds. A rocky planet orbiting in the habitable zone of an active red dwarf fails the atmospheric retention requirement if the star's flare activity erodes the atmosphere during the first billion years of the planet's existence. A rocky planet at the right orbital distance, but with insufficient internal heating, may never generate a secondary atmosphere after its primordial envelope is lost. A planet with a thick atmosphere but the wrong chemical balance may trap heat so efficiently that it becomes a Venus analog, despite sitting at an Earth-like separation from its star. A planet that satisfies every geometric requirement for habitability but orbits a star with intense ultraviolet output may have its atmospheric chemistry continuously disrupted by photochemical reactions that destroy the molecular configurations biology requires. Webb has provided the first direct observational evidence that several of these failure modes are not merely theoretical possibilities, they are active, physical processes operating on real planets right now. Atmospheric stripping on the inner TRAPPIST. One planet is not a model prediction. It is an observational inference drawn from measured thermal emission compared against physical models with real predictive content. Photochemical disruption on WASP 39b is not a laboratory simulation. It is a detected molecular signature in a real atmosphere measured with real instruments. Atmospheric escape on WASP 121b is not a computer calculation. It is a measured outflow observed continuously over a complete orbital period. These processes are happening, and they are happening in ways that reduce habitability rather than support it. The implications of this pattern extend far beyond any individual planetary system. They reach into the deepest assumptions embedded in humanity's thinking about its place in the cosmos, and they interact with a question that has been asked formally for more than 60 years. The Drake equation, formulated in 1961 by the astronomer Frank Drake at a conference in Green Bank, West Virginia, attempts to estimate the number of technologically communicative civilizations in the Milky Way by expressing that number as the product of a chain of factors: the rate at which new stars form in the galaxy, the fraction of those stars that have planets, the average number of planets per stellar system that could in principle support life, the fraction of those candidate planets where life actually develops, the fraction where life eventually produces intelligence, the fraction where intelligent life develops detectable technology, and the average length of time such civilizations remain detectable before going silent. For decades following the exoplanet revolution that began in 1995, the discovery data progressively increased the optimistic estimates for the equation's early terms. More stars had planets than initially assumed, more planets were rocky. More rocky planets sat in habitable zones. Each new Kepler detection nudged those terms upward, making the galaxy seem more populated with potential than previous estimates had allowed. Webb's data now pushes back against the middle terms, the ones that have always carried the most uncertainty and the most consequence. The fraction of planets that could support life depends not just on orbital geometry, but on whether a planet actually retains a functional atmosphere that can maintain surface conditions compatible with biology. And Webb is demonstrating that functional atmospheres may be far less common than orbital statistics alone would imply. If the fraction of habitable zone rocky planets that retain genuinely habitable atmospheres turns out to be 1 in 100 rather than 1 in 10, or 1 in 1,000 rather than 1 in 100, the Drake equation's output drops by corresponding orders of magnitude. The galaxy does not become lifeless, but the expected number of civilizations and the expected distances between them change dramatically. The silence that SETI has encountered across more than 60 years of systematic listening, scanning radio frequencies for signals that have not arrived, begins to feel less like an unexplained mystery and more like a prediction that a harsh universe would make. There is a philosophical dimension to this shift that deserves examination on its own terms, separate from the atmospheric measurements and the Drake equation arithmetic. The Copernican principle has guided scientific thinking about humanity's position in the cosmos for 5 centuries. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of the universe. At every level of investigation, science has moved humanity away from a privileged position, and this progression has been simultaneously humbling and liberating, revealing a cosmos so vast that any fixed center is physically meaningless. The expectation that Earth-like planets would be common was in many ways the natural extension of Copernican reasoning into planetary science. If Earth is not cosmically special in its location, it seemed to follow that Earth should not be cosmically special in its physical characteristics either. The conditions that produced our world should be reproduced across billions of similar planets throughout the galaxy. Abundance of rocky worlds in habitable zones would confirm that Earth-type conditions were a standard outcome of planet formation rather than an unusual one. Webb's emerging results introduce a tension into this reasoning that cannot be dismissed. The conditions on Earth may not be cosmically special in any metaphysical or philosophical sense, but they may be physically rare in a way that carries enormous practical significance for the question of life. A planet with stable liquid water oceans maintained over billions of years, a protective magnetic field strong enough to deflect the stellar wind continuously, a moderate atmosphere chemically balanced between warmth retention and runaway heating, a geologically active interior cycling carbon through the system and regulating climate on geological timescales, a relatively quiet, stable star with moderate ultraviolet output sitting at the right luminosity for the habitable zone to fall at a distance that permits an orbit without tidal locking, a system architecture that keeps the rocky inner planet gravitationally stable. These conditions, taken together, may represent not a cosmically typical outcome, but a specific and uncommon convergence of initial conditions and evolutionary pathways, not unique, not miraculous in any non-scientific sense, but uncommon enough that finding another instance of them, even in a galaxy containing hundreds of billions of stars, may be far more difficult than the mere abundance of rocky planets in habitable zones implied. This is profoundly uncomfortable territory for a species that has spent millennia looking at the night sky and wondering whether someone is looking back. The discomfort does not arise from the data itself, but from the implications of the data for a question that was never purely scientific. The question of whether we are alone is also a question about what it means to exist in this particular universe, on this particular world, looking outward with instruments of increasing sophistication toward a cosmos that keeps revealing itself as stranger and harsher than the dream of cosmic companionship required. The term Earth-like itself needs to be reconsidered in the light of what Webb has found. In common usage, Earth-like has come to mean a rocky planet of roughly Earth size orbiting within its star's habitable zone. By this definition, the Milky Way contains billions of Earth-like planets. The number is real, the detections underlying it are real, but the definition is misleading in a way that has shaped public understanding of the exoplanet field for over a decade, because it equates a handful of gross physical parameters with the full suite of conditions that make Earth not just a planet, but a living world. A planet can be Earth-like in size and orbital distance, and still have an atmospheric pressure 92 times that of our own, laced with sulfuric acid clouds, with a surface temperature hot enough to melt lead. That is Venus, and transit observations from across the galaxy cannot distinguish it from Earth. A planet can be Earth-like in mass and bulk composition and still be tidally locked, with one hemisphere permanently baking under continuous stellar exposure, and the other frozen in perpetual night. A planet can satisfy every observable transit parameter that defines Earth-like by current detection standards and still be a barren, airless rock stripped bare by its parent star over billions of years of cumulative radiation bombardment. If Earth-like is to mean anything scientifically precise going forward, it must incorporate atmospheric composition, surface pressure, temperature stability, stellar radiation environment, and long-term atmospheric retention. By that stricter and more physically meaningful definition, the number of confirmed Earth-like planets in the exoplanet catalogue drops from billions to zero. We have not yet confirmed a single exoplanet with an atmosphere demonstrably similar to Earth's. We have not measured a surface temperature consistent with persistent liquid water on any rocky world beyond our solar system. We have not detected the combination of atmospheric gases that would robustly indicate an active biosphere on any planet. The most Earth-like planet we have ever directly studied in atmospheric detail remains Earth itself. This is not cause for despair, it is cause for precision. The universe is under no obligation to be comforting, and science does not exist to confirm hopes. It exists to describe physical reality. Webb is describing that reality with more fidelity, more depth, and more honesty than any instrument that came before it. And the reality it describes is a cosmos of extraordinary diversity and overwhelming physical severity, where planets form abundantly and conditions for life, as we understand it, appear to require a degree of specific physical circumstance that the sheer number of planets does not automatically guarantee. The silence from SETI is not merely a puzzle about whether technological civilizations exist and choose to communicate. It may reflect something more fundamental about the rarity of the conditions under which any life at all, technological or otherwise, manages to persist long enough to leave any mark on the universe. If habitable atmospheres are rare, if the filter between rocky planet and living world is tighter than the optimistic narrative acknowledged, then the absence of detected signals from other civilizations is not anomalous. It is what the universe would produce, a galaxy full of planets, almost none of them talking, not because intelligence is impossible, but because the road from rocky world to inhabited world is longer, harder, and more demanding than the abundance of planets ever implied. There is also a more personal dimension to the recalibration Webb demands. The knowledge that Earth's conditions may be unusual rather than typical changes the texture of the awareness of being here at all, not in a way that requires philosophy or religion to process, but in a purely physical sense. The stable atmosphere above you right now, the liquid water in every ocean and river and cloud formation, the moderate temperatures that permit biology to function across every latitude and elevation, the magnetic field threading invisibly through the planet deflecting charged particles that would otherwise gradually strip away the air, the geological cycling of carbon that has regulated climate through 500 million years of complex life. These are not default cosmic conditions. They are the outcome of a specific history on a specific world around a specific star, and Webb's data, more than any previous evidence, makes that specificity feel real rather than abstract. The universe did not become less interesting because of what Webb found. It became more honest, and the honesty, as honesty often does, arrived with consequences that take time to absorb fully. The planets are out there, billions of them, real and measurable and strange and magnificent in their diversity. And the familiar ones, the ones that might feel something like home, remain stubbornly, perhaps beautifully, perhaps heartbreakingly uncertain. The search will not stop here. It cannot stop here. The question is too fundamental, the tools are too powerful, and the stakes are too consequential for humanity to accept the current picture as the final word. What Webb has delivered is not a verdict. It is a clarification. A precise and often painful clarification of exactly how difficult the question is, how much more demanding the physical reality of habitable worlds is than the geometric simplification of the habitable zone ever captured, and how much further the investigation must go before anything approaching a definitive answer can be claimed. The search continues, but it continues now against a backdrop that Webb has permanently altered, and understanding what that altered backdrop means for the future of the inquiry is essential to understanding what the inquiry is actually for. Future telescopes will push this investigation into territory that Webb cannot reach. The most ambitious of these proposed instruments is currently known as the Habitable Worlds Observatory, a concept in advanced development at NASA, representing the most direct and deliberate attempt yet to answer the question that Webb has sharpened into its clearest form. Unlike Webb, which studies exoplanet atmospheres primarily by analyzing starlight during transits, the Habitable Worlds Observatory would use a large space-based coronagraph, an instrument designed to block the overwhelming glare of a parent star with extraordinary precision to directly capture the reflected light from small rocky planets orbiting at distances comparable to Earth's separation from the Sun. This is something Webb fundamentally cannot do. Webb excels at transit spectroscopy, which requires a planet's orbital plane to be aligned so that the planet passes between its star and our line of sight as seen from Earth. Only a small fraction of planetary systems have this geometric alignment by chance, and transit spectroscopy works most effectively for planets orbiting close to small stars, which is precisely the planetary category where Webb's observations have found atmospheric stripping to be most severe and atmospheric retention to be most uncertain. The Habitable Worlds Observatory would sidestep these constraints entirely by targeting rocky planets around Sun-like stars at Earth, equivalent orbital distances, the planetary category, where atmospheric retention is physically most plausible, but where transit observations are least feasible because the orbital alignment probability is low and the transit signals from such distant orbits are vanishingly faint. By directly analyzing the reflected starlight from these worlds, the Habitable Worlds Observatory could search for the spectroscopic signatures of oxygen, water vapor, ozone, and methane in their atmospheres. These four molecules, present together in Earth's atmosphere, constitute what astrobiologists call a biosignature combination, a chemical fingerprint that is difficult to produce and maintain without active biological processes continuously replenishing the unstable components. Oxygen reacts readily with surface rocks and atmospheric gases. Without continuous biological production, it disappears from an atmosphere on geologically rapid timescales. Methane reacts with oxygen and is destroyed photochemically. Without biological or geological sources constantly releasing it, it too vanishes. The simultaneous presence of both oxygen and methane in a planetary atmosphere is chemically unstable, requiring an active source to maintain against the thermodynamic tendency toward equilibrium. On Earth, that active source is life. If the Habitable Worlds Observatory detects this combination on a rocky planet orbiting a Sun-like star at an Earth-like distance, the discovery would be among the most consequential in the history of science. Not proof of life. Science does not work in proofs, but evidence compelling enough to demand explanation. Evidence that would reshape every subsequent conversation about humanity's place in the cosmos. The telescope does not yet exist. Its design is still being refined. Its funding has not been secured. Its launch date remains uncertain and probably lies decades away. But the scientific case for building it has never been stronger, and Webb's findings are a significant part of the reason why. Because Webb has demonstrated with unprecedented clarity exactly what kind of instrument is needed to answer the question that detection alone was never equipped to answer. The extremely large telescope, currently under construction in the Atacama Desert of Chile, along with other next-generation ground-based observatories, will contribute higher-resolution spectroscopy of brighter exoplanet targets, probing atmospheric compositions with a precision that complements Webb's space-based observations. The Nancy Grace Roman Space Telescope will survey thousands of exoplanets using gravitational microlensing, a technique that reveals planets at wide orbital separations around distant stars, filling in the population statistics of planetary systems at distances that neither Kepler nor TESS could adequately probe. Each new instrument will add layers of information to the picture that Webb has begun assembling. Each layer will further narrow the distance between what is detected and what is understood. But the fundamental lesson that Webb has delivered will not be reversed by more powerful instruments. It will be deepened. The lesson is that alien worlds are not simple. They are not waiting to be recognized as variations on a familiar theme. They are products of chaotic formation histories, shaped by intense and prolonged stellar radiation, governed by exotic chemistry, sculpted by physical processes that produce environments ranging from merely inhospitable to spectacularly violent. The universe creates planets with extraordinary efficiency. It creates habitable planets, as far as the best instruments humanity has ever built can currently determine, with far greater reluctance. There is a deeper lesson embedded in the trajectory of exoplanet science from 1995 to the present. One that goes beyond the specific findings about atmospheric composition or stellar radiation or habitable zone statistics. It is a lesson about the difference between detection and understanding, and about how dangerous it is to allow the former to substitute for the latter in the stories we tell about the universe. For 2 decades, the exoplanet field advanced primarily through detection. Thousands of planets were found, catalogued, categorized, and assigned habitability scores based on size and orbital distance. This was necessary work. It was genuinely valuable work. The catalogue represents one of the great scientific achievements of the era, but it created an illusion of comprehension that the data did not actually support. The catalogue felt like knowledge. The statistics felt like understanding. The habitable zone felt like a meaningful physical descriptor, rather than a geometric simplification that captured one necessary condition while ignoring dozens of others that mattered just as much. Webb revealed that detection without characterization is something like reading a list of addresses and believing you know the people who live at them. The addresses are real, the buildings exist, but you know nothing about what is inside, what the conditions are like, whether the structure is sound or crumbling, whether anyone could actually live there. Webb opened the doors of alien worlds for the first time, and what it found inside was not what the list of addresses had prepared anyone to expect. The term potentially habitable, used so freely across 2 decades of exoplanet announcements, deserves to be retired or at least fundamentally reconsidered. Potentially habitable implied that the primary obstacle to confirming habitability was instrumental limitation, that better telescopes would reveal conditions broadly consistent with the optimistic inference. What Webb has shown is that the obstacle is not primarily instrumental, it is physical. The conditions that define genuine habitability are demanding, specific, and apparently uncommon. Better instruments reveal this with greater precision. They do not dissolve it. What replaces potentially habitable in the vocabulary of planetary science going forward must be more honest about what is known and what is not. A planet can be described accurately as a rocky world in its star's habitable zone with an uncharacterized atmosphere. That is a precise and honest statement. It says what is known, identifies what is unknown, and makes no inference beyond what the data supports. It is a less emotionally satisfying phrase than potentially habitable. It does not invite the same imaginative projection. It does not generate the same headlines, but it is what the science actually says. And after Webb, the science deserves to be described as what it actually says. The search for life beyond Earth will continue. It must continue. Not because Webb's findings make that search easy or promising in the near term, but because the question it addresses is too important to abandon on the basis of early returns, however sobering. Every generation of astronomers has worked with the best instruments available to it, and has found the universe more complex than the previous generation anticipated. The generation working with Webb is finding alien worlds more extreme and more alien than the generation working with Kepler anticipated. The generation that will work with the Habitable Worlds Observatory, if it is built, may find things that the current generation has not yet imagined. Science does not move toward comfort, it moves toward accuracy. And accuracy, applied to the question of whether life exists elsewhere in this vast and ancient universe, is worth pursuing regardless of where the evidence leads, regardless of how many hopeful narratives it complicates along the way, regardless of how many artist renderings of blue and green alien worlds it renders obsolete. There is something worth sitting with in what Webb has found, something that goes beyond the specific atmospheric measurements and the revised habitability statistics and the contested biosignature claims. Something about what it means to be the kind of creature that builds these instruments at all. Consider the chain of events required for the observations described in this account to exist. A rocky planet formed 4.5 billion years ago in the outer disk of a moderately sized spiral galaxy. Over hundreds of millions of years, it cooled, and water arrived, and chemistry organized itself into self-replicating structures. Over billions of additional years, those structures grew more complex, developed sensory apparatus, developed nervous systems capable of modeling the external world, developed language to share those models, developed writing to preserve them, developed mathematics to formalize them, developed physics to describe the laws governing the universe at every scale, developed engineering sufficient to fabricate a mirror 6.5 meters across from 18 precisely shaped beryllium segments coated in gold to nanometer tolerances, launched that mirror into space aboard a rocket, deployed it at a point 1.5 million kilometers from its origin world, cooled its instruments to temperatures just 40 degrees above absolute zero, and used it to measure the chemical composition of the atmosphere of a planet 700 light-years away by analyzing the fractional dimming of starlight during a transit lasting a few hours. That chain of events is, by any reasonable measure, more improbable than any of the alien worlds Webb has examined. The instruments that found those worlds to be harsh and strange and nothing like home were built by something that emerged from precisely the kind of conditions those instruments are struggling to find elsewhere. The irony is not lost. The beings most invested in finding another Earth are themselves the most extraordinary evidence that Earth's conditions produce something worth finding. Webb did not shatter the dream of finding another world like ours. It clarified the terms of that dream with a precision that no previous instrument could achieve. It showed that the dream requires not merely a planet of the right size at the right distance from a star of the right luminosity. It requires an atmosphere of the right composition maintained by the right geological processes against the right stellar environment over the right timescales, with the right magnetic protection and the right orbital stability and the right chemical history. Each requirement narrows the field of candidates. Each narrows it further than the one before. And the field that remains, while it may not be empty, is smaller and more demanding and more specific than the vast optimistic landscape that detection alone once seemed to promise. When you look up at the night sky on a clear evening, you are looking at a galaxy that contains, by conservative estimate, hundreds of billions of stars. Many of those stars are orbited by planets. Some of those planets are rocky. A fraction of those rocky planets sit at distances from their stars, where liquid water could, in principle, exist. The numbers remain enormous. The possibilities remain real, but Webb has added a weight to those possibilities that changes how they feel. Not the comfortable weight of statistical inevitability, of a universe so large that Earth-like worlds must exist somewhere by sheer arithmetic necessity. A different weight. The weight of physical specificity. The weight of knowing that between a rocky planet existing and a living world existing lies a distance filled with atmospheric chemistry and stellar radiation and geological history and magnetic fields and 100 other variables that can all go wrong in ways that the geometry of the habitable zone was never designed to capture. The planets are out there. Webb proved that with greater clarity than any instrument before it. And most of them, as far as the most sensitive infrared observatory humanity has ever constructed can determine, are places of extraordinary physical severity where the chemistry is alien, the temperatures are extreme, the atmospheres are absent or hostile or caught in cycles of creation and destruction, and the resemblance to anything a human being would recognize as home is thin to the point of vanishing. The universe did not become less interesting. It became more honest. And somewhere in that honesty, in that vast and largely indifferent darkness populated by worlds that burn and strip and freeze and churn without regard for any observer's hopes, there is this. One world that did not go wrong. One atmosphere that held. One magnetic field that deflected enough of the wind. One geological engine that cycled carbon through the system for long enough. One star that burned steadily rather than violently. One rocky planet where the conditions that Webb is struggling to find anywhere else simply persisted and accumulated and eventually produced something capable of building a golden mirror and sending it into the dark to look. The warmth is here now. on this world, in this moment. It is extraordinary, it is temporary, and it is ours.